In this video, we are going to discuss about multicollinearity. That is a particular feature or particular property of a design matrix that often plagues a real-life situation. In order to understand that, let's start with the simple setup. So we have this Gauss-Markov setup where we have this y equal to x beta plus epsilon, and epsilon follows 0 sigma square I. Now we know that in this setup we have our least square estimator, which is beta hat equal to x prime x inverse x prime y, and the covariance matrix of this estimator is sigma square x prime x whole inverse. Now these two expressions remind us that it is very important that x prime x should be invertible, otherwise this inverse will not exist, and that means that x should be full column rank. Now in many situations we see that x is not, it is full column rank, but it is very near to being not full column rank. That is, some of the columns of x are approximately linearly related. For example, one column may be twice another column plus a little bit of jitter. Something like if you have measured the same heights in centimeter as well as inches, then one will be 2.54 times the other, with a little bit of error because of measurement error. So they are very closely related. Whenever that happens, our x prime x matrix becomes very close to being singular, and this situation is called multicollinearity. And you can easily understand that then problems will arise. In particular, this covariance matrix will start becoming very large, in the sense the variances will be very large. How to understand that a particular data set is plagued by multicollinearity? There are a couple of ways to diagnose the problem. The first of them is called variance inflation factor. The idea is, if you find that your estimated coefficients have very high variance, very bloated variance, you begin to suspect that multicollinearity might be present. How do you measure that? You just look at what are called the VIFs, which are basically nothing but the diagonal entries of your x transpose x whole inverse matrix. So VIF times sigma square will give you the variance of beta I hat. That's why it is called variance inflation factor. So the variance of epsilons is sigma square. You are inflating it by this amount in order to get the estimate of beta I hat. If these quantities are very high, or at least some of them are very high, you suspect multicollinearity may be the culprit. Now sometimes you can feel that multicollinearity is present when you have a model, and from your domain knowledge you know, or you have a very strong gut feeling that certain variables should be significant, but you find that they turn out to be insignificant. For example, you are trying to regress, say, weight on height, and you find that height turns out to be insignificant. In that case, you suspect multicollinearity is present. For example, if you collect your data set like this, you measure weight in kilogram, you measure height in inches, and you also measure height in centimeter, but because of some measurement conversion, some unit conversion round of error, they are not exactly 2.54 times each other. In this case, you might find that the significance of the coefficient of height, either in inches or in centimeters, happens to be pretty low. So it turns out to be insignificant. That is because the variance term is very high, and when you are computing the t statistic or their statistic, you are dividing by the variance or the standard error. So you are dividing by a large number. As a result, your test statistic becomes very small, and the estimated coefficient becomes insignificant. So when you see this, that is another reason to suspect that your data set might be plagued with multicollinearity.